So, it's my pleasure to welcome Larry. Please.
Okay. Thank you, Nicholas. All right, we've got the eye, which I always like to show first, but there we go. So, thank you very much, Nicholas, for inviting me. My name is Larry Kaplan. I'm the Chief Software Architect for HPC and now AI solutions at Hewlett-Packard Enterprise, coming from Cray. You know, it was kind of interesting that Nicholas asked for this original little biography. So number one, I am not the video game developer. Apparently there is a famous Larry Kaplan video game developer. That is not me. I am a longtime HPC systems and software specialist. You can see, I'm not going to read through all of the different experience that I've been through. But what I will comment on are these pictures, which I will not be posting. The one on the top is the delivery of the TC2000, which was the first machine for the attack of the killer micros at Lawrence Livermore National Lab. And the gentleman in the red shirt there on the left is Eugene Brooks. And then, of course, you can see me over 30 years ago. And you can draw your own conclusions.
You were told.
Apparently I'm taller. Well, the guys sitting down were taller than me, which is, I think, why they were sitting, because Eugene was not a tall guy. Julie Chow in the middle was the lead hardware architect for the program. The other, I think, thing just to point out, right, I am an avid water skier. That is me just a couple of years ago. We have lovely water skiing in Seattle if anybody wants to come visit. For the posted version, we'll just show some machines. So the TC2000 Red Storm, and that's actually Blue Waters on the bottom, the NCSA machine that had one of those difficult histories. And we can talk about that some other time if folks would like. Okay, so let's move on. So I guess I wanted to start with just some context. So I think folks know through whatever eventualities that have occurred in the marketplace and in the business community, HPE is now really dominating in the high-end supercomputing. It's really built on HP expertise, which has really been, a lot of it's been inherited from both Cray, SGI, and some former HPE efforts as well. And we bring together a combination of a bunch of different technologies to provide these end-to-end solutions. So we do have our own networks. We use the best of the available component vendor processors. We have the software that brings it together, and then we also do provide storage solutions. We have recently added the Deos team. So we are now supporting Deos in addition to Lustre. So we do provide these complete solutions, and we've had some great successes recently, as I think folks know. So these are the top 3 machines on the top 500, as was stated before. We don't know what else is out there if they didn't report, but at least for now, these are the top 3 machines built with somewhat different components. The other thing I'd like to say about these machines, though it's not quite so true for the middle one, is that these are not snowflakes. These are not one-offs. These are products. Anybody can come and give us an order, and we will deliver these to you. And in fact, for the ones on each side, there are many instances. If you look on the top 500 list, you will see down, below that top 10, and even within, I think for a couple of them, they're just smaller versions of these same machines. They're products. The other thing that we have done is starting to do the AI. So we saw from Simon before, the one on the right here, and we've also got a few other ones that we've been working on with some other customers. So the CSCS machine, Alps, Los Alpes Machine Venado, these are focused more in the AI space. So it's definitely something that we have turned our gaze towards, not without challenges. And I'll be talking about some of those challenges as part of this talk. So it's, we're going to focus on these effective and efficient complex workflows, which include both AI and HPC. Obviously, we have years of experience in HPC, It's where AI is that we have to start worrying about it. So, and make more progress. So what I'm going to show here may look somewhat familiar to folks. They may see bits and pieces of things they've worked on in their own workflows. This is not actually meant to represent any real one workflow. It's what I like to call the amalgamated workflow. It takes, basically it's a mashup of of a bunch of potential components in a workflow. But what it's meant to show is the fact that there are a bunch of different pieces that one might want to run, not only on individual systems, but across multiple systems. So we've heard several talks already about the idea of edge integration, both from the point of view of farming, also from scientific instruments, light sources and such, and the need to do potentially pre-processing over on those components, those edge devices. We want to start introducing AI. Now I have on the bottom dashed some of the AI components. The ones on the top really is more about steering, not AI. But then we get to traditional HPC. Again, doesn't have to be a linear pipeline here, though it looks like one down the bottom. And then we have this challenge of data transfer. How do we actually communicate between these components that has already been raised? So there's presenting challenges even just there. So we have the idea then of, besides just simulation, how do we apply AI? Well, we've got these surrogate models, the idea of being able to accelerate pieces of the applications. And all along, you have to be able to monitor this stuff, look at performance, look at progression. And then we might take the output over to a more AI ML-based system. Again, could be on one of those other machines we just talked about, could be elsewhere. And then there may be some additional training and then potential feedback loops, whether it's steering of the actual experiments. I think Raphael's going to talk more about doing that edge control. But you also have the possibility of doing simulation steering. So the idea here is there's a lot of different complicated relationships you may have from these workflow components. And we want to try and figure out, well, how do we deal with this environment from both being effective, being able to think about it and program it and reason about it, but also making it efficient. So I'm going to look at a few things, and this is not meant to be exhaustive. I'm trying to focus on the pieces that I'm able to address in the amount of time we have. And I'm looking at not necessarily the application level here, but what is required in order to provide the applications the necessary infrastructure. And it's not just the applications, it's the users as well. So if we look over on the left-hand side, we talk about infrastructure. We'll note that a lot of these workflows are actually coming in from the cloud. Well, and the cloud access is a different thing than HPC access. And so how do we make the access flexible in the way that these users are used to, right? That's not what HPC has done traditionally. HPC traditionally is you submit a batch job. Well, that's not going to work here. And so we need to figure out how to address this. We also have different types of service models. I'm not going to talk here about infrastructure as a service. That's really a little bit too low level for what I want to do. But platform as a service, software as a service, those seem to be very relevant models for how I want to compose these workflows. Platform in terms of providing, whether it's a virtualized platform or a bare metal platform that is comfortable for the user to run that application component. And then software as a service potentially, whether it's serving up models, serving up other types of services. These are all things that we think are important for what we're going to be seeing in terms of future workflows. And really, if we go all the way, we could go to function as a service. Now, function as a service, where you're using pieces of components, pieces of nodes across different applications, does present additional challenges. So that's something maybe that's a little further in the future, but we'll talk a little bit about that as well. And then finally, we get back to efficiency. We really want to understand how to make the best use of the resources, power and energy, and it turns out there's also ways to optimize capital investment here in order to better efficiently support these workflows. So I'm going to be digging into these topics. This is just to point out what are the challenges that we're facing. So moving to the second one, we've talked about, I think some folks have mentioned containers in various ways. Again, containers are heavily used in this space. It's starting to show up in HPC as well, but it's already heavily there more in the AI space. So we need to provide the tools in order to be able to use them effectively, and also potentially have some options in orchestration. Again, traditional HPC is batch. We believe there is a place for Kubernetes. Some folks are getting very interested in that, even on their supercomputer platforms. And then finally, the workflows themselves. How do we allow the domain scientist and potentially the computer scientist that's helping them, that doesn't really want to understand the details of what's underneath, but they may have their own domain-specific workflow management engine that they need to be able to drive the workflow. How are they going to do that? There's some options there. We have seen some evidence of stuff out there already that's working, but there are some challenges there as well. When we deal with the scheduling problem, yeah, of course, you're going to be scheduling processors and nodes, but there's more, especially when you're talking about these complex workflows that you're trying to essentially, in some ways, isolate and provide quality of service guarantees separate from anything else going on in the system. So we'll talk about that as well. And then I mentioned services. These are private. These are workflow private services. So we've already heard some examples. I think that Kafka-like interface for a streaming service within a workflow is a really good example. There are some other ones that I think we want to touch upon here as well. Okay, so that's from a workflow standpoint, but then when we go into the sustainability, we have a bunch of concerns as well that we also want to be looking at. And you have a few different ways of looking at it, and there's some overlap here, but the point is, ultimately, you want to get the best performance both per watt and per joule. They have different implications. And the way we tend to think about it is when you're talking about watts, you're talking about CapEx. When you're talking about joules, you're talking about OpEx. Both are relevant, and we're going to talk about that in more detail. There's also these desires, really. There are other things you may want to do. You want to deal with, do you want to reuse your heat? Some folks are looking at that, though they didn't say it in the room, but okay, I got a nod over there. So Simon is looking at that. So we do have customers who are interested in, let's use the heat to heat a town. Let's not just throw it into the atmosphere. Let's do some things with that. And then there's some other things, can you do cheaper cooling? So chillerless cooling, how do you deal with those kinds of things? So these are all kinds of things we want to address. So we've been working on a bunch of different software. A lot of this software we consider to be actually at what we call the user services level. So figure it's sort of operating system level. There's some tendrils into system management when you're talking about power and energy. But when you're really talking about the workflow stuff, this is not a system administrator thing. Doing scheduling, doing deployment of services, we'd actually consider to be something that's part of the managed ecosystem. And so the software here really is focused on the managed ecosystem. So there's a few examples here. I've talked about a few of these things. So we'll be looking at this enabling of these diverse workflows, what we might do for containerization, looking at what it means to Linux distributions. We've talked about, I mentioned a little bit about the power management, and I'll go into detail what we can do there. There was the discussion of, well, what about AI profiling, ML profiling? Well, we would love to do something there as well. That one's more of a programming environment thing, but there are things we can do for optimization at the application level without getting to that level, which I'll also try and touch upon. Over on the efficiency side in general, so the orchestration, understanding these scheduling domains, doing these transfer operations. One thing we do have today is this low noise mode. So I was actually kind of interested in the talk earlier today when we were talking about NUMA. The idea of running anything that has background activity on an HPC node that is not directly involved in the application, such as something like NUMA balance, I think folks know is an anathema on a scalable system. It's the way to destroy performance. And so we have other ways of dealing with that by making sure we properly lay out individual processes that are affine to given NUMA nodes and processors. And then we have additional work, which the community provides. The Linux community does provide this, that if you make the right settings, you can really eliminate a lot of the noise on your nodes so that they are working to progress the application and nothing else. Now, AI space and Kubernetes, that's going to make things a little bit interesting as we go down those paths. I probably won't touch upon that too much today. Okay, so let's dig into some of how we want to address these things. What are we looking at to address all of these things? So virtualization. So virtualization provides a bunch of benefits. You can do containers without virtualization. There are plenty of good things you can do that way, but there are times we may want to actually use virtualization as well. Isolation is one reason. Some people are looking at it for using for resilience. It provides a better migratable container if you're looking at resilience. That's another thing that we tend to do at HPE. We're interested in scale. Well, when you're at scale, reliability is a concern. What are we going to do about it? Virtualization may give us some things to help with that. There's also this idea of fully confidential computing and dealing with trusted workloads where you really are trying to get to zero trust. And by zero trust, we mean not only cannot other users and other groups see what's going on, but even your administrators can't see what's going on. So this is something that we think is coming down the pike that we're going to need to deal with. We already see it to some extent with certain workloads, but right now, the system administrators tend to be allowed to see it, but ultimately the goal is to not need that. And then I had mentioned function as a service before. If you're going to be sharing these nodes, especially between different users and different groups, virtualization will hopefully with confidential computing provide you that necessary isolation. So something, again, we're looking at, we hope we're going to get to the basics fairly soon. How much further should we be going? And by the way, I really, took Nicholas to heart here. You can see what I'm proposing, what I'm talking about here, a lot of it is proposed and not here today. And so please, I want to hear your feedback, and it doesn't have to be right here, offline, after the talk, during the rest of the work of the conference. We're looking for feedback. Are we on the right track, or are we spending time on things we shouldn't be? So please keep that in mind as I go through it. Okay, so that was virtualization. Mention the workflow services. So, private databases, private event buses, maybe private streaming, tracking for the various transfers, the various progressions that you may need to do so you can do event-based workflows. That seems that's a potential way to ease the automation of workflow deployment. So it's something we want to look at. Service resiliency, I mentioned before. How do we make sure that these, you don't have a failure of any of these services in the middle of your workflow? And then we talk a little bit more about then extending this. So we have the data management, extending the workflow tracking and management so that it's not just within one system, but then it's actually across federated systems. And I want to be clear here, when we talk about federation, and I'll say more about this in a little bit, we don't want it to be required as much as we would like to, that it's always HPE equipment. We realize the reality that we can't, rule the world. As much as we would like everything to be bought from us, we want to be able to interoperate. And so I think that's really important. And it's interoperate not just with other vendors, potentially with the cloud. And so that's part of what we're looking at here is how we do this across sites and facilities potentially. So we talked a little bit about composition tool. We talked about the profiling, potentially some debugging. This other one, an integrated quality of service. So this is where, so again, you can sort of do quality of service based upon how you do scheduling priorities within your various schedulers. Batch and Kubernetes both have ways of doing that. But what about the rest? What about networks? What about storage? Well, networks have quality of service settings. How do you make them easy to access? How do you set up say a workflow private VLAN that then has quality of service guarantees and take that all the way to your storage devices? These are things that we think will be important. We'd love to get feedback on. So that's services. Runtime. So here, how do we glue the two worlds together? So we do have a project. This is not a product. So this is a project called Dragon, which that is its goal. Folks may have also heard of SmartSim, which was also a project that was done at Cray and HPE earlier. I believe they've all been folded together now. But the idea is in a Python environment, can you set up these conduits that are effective for communication between AI and HPC components. There's a lot of details there. We do have some proof of concepts that are out there. Again, today, this is a project. There are some links. These slides should be posted, so no worries about pictures. They will be. Just that one picture of me won't be posted. But these will be posted. So again, we think this is good. We have not committed to productizing this. We will continue to work with the community on this, but how far should we really be going? All right, and then finally, the other big thing in terms of the workflows is this idea of having a common federation API for these complex workflows. And so I've actually presented this a couple of times already. We are still trying to gain some momentum here. And so again, interest is important. You'll see I do have the advanced photon source that one of my colleagues put on this slide for me. There you go. But the idea here is you'll have these topics, and so you can see the 6 topics across the top. The workflow topic would be how you access these services that you might need, whether it's databases or event buses, and configure those, or even this Kafka-like API you might set up there. Schedule is going to be your typical, scheduling batch, Kubernetes. Maybe you're going to schedule with some other external entities, meta-schedulers or whatever. We're open to it. And I'll say a little bit more about the context after I go through the topics. Data is for data transfer, so regular streaming, store and forward, those kinds of things. Metadata, well, I would really like to track what the data is that I'm transferring. Do I have provenance on that data? Do I know what it's really about? So there's a bunch of things we would like to do there. I would say that one's probably the furthest out right now in terms of research. So those 4 are really the ones that we think would face the user. But in order to enable what faces the user, we think we also need to have an administrative interface, and that's what /fleet is. So the idea here is that the administrator would be able to configure what is exposed on those other interfaces, and then maybe it's a user read-only interface so that they can query to see then what they have access to with these other interfaces. And then finally, of course, all of this has to be covered with authentication and authorization. And we believe it's both for human and non-human, non-person entities. Machines have to trust each other when they're talking in a federated manner. And then, of course, we have to know who the users are who are using it. So, someone might say, well, you're reinventing the wheel. We have stuff like this. And indeed, there are examples of APIs like this, or at least subsets of this, already out there. Superfacility, Intersect, there's a few of them out there. I think Firecrest would be another one. We don't propose to subsume these guys. We want to just unify everything. And so the idea would be that if we were able to bring the community together to do something like this, any site that's using their own API, we would then just map to these APIs. We would provision these APIs. Other vendors, hopefully cloud providers, could provision these APIs. And then users could either code to them directly, or we would have translation layers from individual site-specific APIs, because we believe there's sufficient commonality and sufficient similarity to what these APIs want to do. We expect them to be RESTful, which these examples I was giving already are. So we do see that there's a path where we can be a unifier rather than a divider here. But it's going to take participation to do it. Okay, so that's the workflow focus and what we're looking at. And let's move to sustainability. So today, we do have in our system some advanced power and cooling management, where we're able to really do some fine-grained work in the various pieces of the system. And you can see some examples here. I won't read through it. And part of it, of course, is doing some monitoring and analysis of the data, of the power and energy data that's coming through the system. And then the question is, what do you do with it? Well, you can do some power steering. We have some rudimentary power steering. We have the ability to do power management at certain levels. So here we're talking about per user, per group, per job controls, and account for all that consumed energy. So when someone wants to know about it, we can tell them. I think one of the challenges, and I think it was mentioned earlier yesterday, that how much are the users really going to care about this if you're just charging them for core hours? Shouldn't we start charging them for joules? Well, a lot of the sites really don't charge their users for anything. It's just all funny money. But maybe the accounting could be done via energy versus via time. And then this would become more important and more realistic as to the resources that are being consumed. There is something for occupancy to be said for charging for occupancy, but I think energy, people will agree, is also a very big component. So then we also have the ability today to do some power capping. You might have some rudimentary reasons to do the power capping, whether it's environmental failures, you lost a power feed, you lost a chiller, you're in California and they're doing a brownout, stuff like that. Still very basic types of features today. We do also have some AI operations. So I think one of the other things that I was noticing, it's not just HPC on ML and ML on HPC, it's also ML to operate HPC. Both from a system management standpoint, we're also looking at expert advisors for tools, things like that. And so this would be an expert advisor for system administration. And actually, we do have this capability today, some basic capability today. So where do we want to go? Where we want to go is to allow at both levels, both the system administrator level and the user, to help us define the optimization policies. And we want to use that to actually make it so that you don't over-provision your system. If you look today, what you'll see is that most systems are provisioned in their data center for nameplate power, and they never use it. Now in AI, it's a little less true. You tend to get closer to the nameplate power, but in HPC, unless all you do is run DGEM, which I don't think anybody does, you're not. So why? Why would you provision all that power? What can we do about that? And again, we want to give this a little bit more control, depending upon whether it's external conditions or just a desire to optimize workloads, for both the administrator to help decide exactly how the system should be operating. But we also want to give this to the user on a per application basis. So we do have a proof of concept that's showing some good energy savings, talking about 10, 20% on both HPC and AI workloads at only a 1 to 2% performance loss, where there's no user burden. The user just sets the dial, and then by doing external monitoring of the application, we can see what power is being used where and make sure we change where the power is being delivered. So again, this can be done both at the system level and at the job level. Right now, I'm going to focus a little bit more on the system level. So this is an example, a TCO savings example. It's based upon some theoretical 200 kilowatt racks, which we believe are coming down the pike. And we've got 8 of them. And so that's where you get, the 8 times 200 kilowatts, you get the 1.6 IT compute power megawatts there with no management. So let's see, yep, right there. And then the facility power is going back to all that crazy PUE and all that those, let's see, what is it? It's PUE, ITUE, and some other crazy formulas that I don't fully understand, but my power architect does. I think other people in the room probably do, but you have overheads involved in delivering that 1.6. So if you just look straight, and then you look at, again, cost, this is using US costs, how much it would cost to operate that for 5 years, and you haven't done any optimization yet. So the state of the art today would be to just do a uniform static power capping, and we're choosing just sort of an arbitrary level here of a 25% power cap, which obviously gets you down to 1.2 megawatt of IT power. But then if you say you're going to do that and you're always going to operate your system that way, well, don't provision your data center for 1.6, provision it for 1.2, and you've just saved a CapEx savings. You didn't really get an OpEx savings because you were never consuming the power in the first place. But you do get this CapEx savings. Now, if we apply a more dynamic power management strategy, and to do so, it does require an application mix. If all you're doing is running DGEM, or all you're doing is running the highest power AI applications, this isn't going to work. But for most of our customers and most of the large HPC sites, they do run a job mix. And so with that job mix, we know that we don't need to provision full power for every application. We can provision the full power for those that need it, but then not provision it for those that don't, cap them. And so then we can get the same CapEx savings, but with much better performance, overall performance. So we don't lose the performance. So then we add the additional ability then for the administrator and potentially the user to adjust that slider and say, well, you know, I'm willing to give up a little performance if I can get some of that OpEx savings. And that's what we're showing in the second and third column, I'm sorry, in the next to last and the last column with two different settings. So the first one is the 95% setting, don't lose more than 5% performance. The next one is don't lose more than 10% performance. And then you see the resulting benefits in terms of the savings. So again, this is stuff that this is more stuff we're looking at right now. We are looking at deploying this in future systems. The previous page is available today. This page is for the future, but we believe this is something that customers would be very interested in. And then you can take into account, this is only taking into account the TCO part, but as I mentioned, you can also take into account other things. Do I need to do anything extra if I don't have the same kind of cooling, where I have to deal with weather events because it's going to change my cooling, or if I have to maintain a heat output because I'm doing something with that heat? These are all other potential inputs into a power management system. So I did kind of whip through that. I actually have a couple more slides I could go to, but maybe let's just keep going and we'll do questions. But then just to summarize, so we've gone through some challenges in the complex workflow and AI support and what we might do. I didn't mention the Linux distributions. I'll just say a little more about that. So, you know, as we know in the AI space, there are certain distributions that are more favored than others. We recognize that, and we're going to move to support them. So that's something that's very important. I think I've touched upon most of the rest here, all the way down. But again, this is the summary. So, you know, scheduling, different types of scheduling. Maybe there's ways to actually have dynamic resource management and sharing across those scheduling domains. Things we want to do in containers and virtualization to support portability and isolation. These workflow services and the unified API. And then in power management, the various use cases. And again, ultimately, one of our main goals here is to lower total cost of ownership. And I think I will stop there.